Hello YouTube, welcome to my channel. My name is Tony and today we're going to cover Minimax algorithms from Leetcode. And in this video, we will summarize 8 problems from Leetcode, and this will cover 80% of the Minimax algorithm from Leetcode. So if you understand all of them, so you understand the core idea of what is Minimax. So without further ado, let's just go ahead and check what is Minimax. So Minimax algorithm is one of the subtype algorithm from game theory. So within Leetcode, we typically have two players and playing some sort of games with certain restrictions. So for example, we have two players and playing some sort of games. At each round, each player want to maximize their profits and also want to minimize the opponent's profits. So let's just check one of the example right here. So for example, we have the player 1 and he has two options, and the opponents may have two options based on what player 1 has. And at each round, the player might not necessarily pick the high reward at each round because he want to win the overall game. So one of the examples is right here. So if the player 1 pick the lower reward, for example, this is the lower reward and this is the high reward, and turns out his opponents may even pick the lower reward from the following games, right, following a round, and this causing the player 1 actually win up the entire game, overall game. As you can tell that the local minimum does not guarantee the global maximum. And this is actually the core idea of how we solve the Minimax algorithms. So if you are like experienced developer, you probably notice that, wait a minute. So isn't this sounds like dynamic programming? Yes, you're right. This is actually the solution for Minimax algorithm is actually by using dynamic programming, and we're gonna cover the local optimum and the global optimum in the later slides. So don't worry about it, and we're gonna cover this later. So let's just go ahead and check how we solve the Minimax algorithm. Like we mentioned, so we're gonna use dynamic programming to solve it, and there are typically two ways to solve dynamic programming. One of the option is by using bottom up. So we initialize some sort of array and do some initialization and deal with the corner cases and transformation function. So once you can figure out the transformation function, you pretty much solve the entire problem already. But in this video, we'll mainly focus on the option number 2, which is the DFS, by using top-down approach, by using recursive function to solve the entire algorithm. So the reason I want to focus on the option number 2 is because the base case is much simpler and we don't have to deal with any corner cases. All we have to think about is the recursive function, which is more intuitive for the beginner. And if you have like more experiences with dynamic programming, so you can come back to the option number 1, which is using the bottom-up approach. And this code might look intimidating in the beginning, but don't worry about it. So we're gonna go over the exact details of every line of this piece of code. So let's just go ahead and check one of the concrete example first. So this is a classic problem from Leetcode, and it's well known and predict the winner, right? Given an array of the scores that are non-negative integers, and player 1 picks one of the numbers from the either end of the array and followed by the player 2 and then player 1 and so on. Each time the player picks a number, and the number will not be available for the next player, and this continues until all the score has been chosen. The player with the maximum score wins. So and if you read the question carefully, and this is actually the exact definition for Minimax, right? So when you solve the Minimax algorithms, and there are two things you have to worry about or concern about, and basically there are two restrictions. So one of the restriction is, as a player 1, what's your option? So what are the numbers, or what are the rewards or the values or the profits you can take, and what are the things you can leave out for next player? So what is the next player can play with the entire reward? So that's the only two restrictions we have to concern about to solve the problem. So let's just go ahead and check one of the example first. So the example number 152. So for example, I'm the player 1, so I'll pick for example number 1, and then so player 2 will probably gonna pick 5 because it's the higher reward, right? And turns out I lose the game because even though I pick 2, so 3 will still lower than 5. So it doesn't matter if I start with 1 or 2, the player 2 will also pick 5, and eventually I'll lose the game anyway. So that's why I will return false in this game. And so let's check out one more examples, right? So maybe I'm greedy and I'm still the player 1, right? I'm greedy. I'll pick this number 7, and the player 2 will definitely go ahead and pick 233. And it doesn't matter whatever I pick from the next round, I'll lose the game because 233 is way bigger than any numbers else, right? So it turns out player 2 will actually win the game if I start with a 7. So now let's come back and and check what else I can pick, right? So if I start with 1 and the player 2 can pick maybe 7, and if he picks 7, I'll pick 233 and I'll win the game. Or if I start with 1 and he pick 5, and I'll still pick 233, so I'll still win the game. So it looks like in the beginning I pick a lower number, but turns out I actually win the overall game. So that's what I mentioned in the beginning of the video. The local optimal solution does not guarantee the global optimal solution, and the reason behind it is so there are different variations that we can try out by using Minimax algorithms, and that's what we're gonna go over in the next slides. So before we go to the next slides, and I want to talk about go back to the previous question that I mentioned. So what are the two restrictions that we have to concern about? So one of the restriction is, for example, in this example, right, in this question. So one of the restriction is each player can only pick a number from either left hand side or right hand side. So for example, I'm the player 1. I can either pick 1 or 7, and the player 2 can pick the numbers that I leaving out. So for example, if I pick 1 as a player 1, and the player 2 cannot pick 1 anymore. And that's the core idea for Minimax. So if you think about this question carefully, so if we can pick from the left hand side or right hand side, we probably need to index to indicating that, right? And that's exactly how we solve the question. So let's go to the next slide, and just don't worry about the main function first. I'm basically calling the recursive function, and let's skip the base case and let's just focus on the core idea of the recursive function. And that's what we're gonna do for the out of the following question. Let's focus on the recursive function first. So now let's check the first one. What is the recursive function means? So think about it. So let's come down and think about the problem. So I'm the player 1, so I can either pick from the left hand side or right hand side. That's why I pass 2 index, right? I and j. If you check the I starts from the very beginning of the index, and j stands for the very right hand side of the index, which stands for 5. So I start with the very left and very right as a player 1, and then I want to check, hey, so if I'm the player 1, I can pick 2. If I pick 2, right? So what's my opponents can pick in the next round? So if this is I, this is j. If I already pick 1, right? If I already pick 2, the first index, right? And my player can only pick 3 all the way to 5, right? So if that's what my opponents can pick, and then so isn't this is actually the index for my opponents if I pick from the very beginning? And now if I pick from the very end, let's say 5, right? And my opponents can only pick from I all the way to I, j minus 1. And this is right here. This is j, and this is going to be j minus 1. And this is what my opponents can pick. And now let's go into the core idea for the restriction. So my number, my reward in the first round could be from the very left, which is nums I, minus what my opponents got, which is right here, the recursive function we indicated with a variable. And if I pick it from the right hand side, which is 5, and my opponents can only pick from the recursive function right here, which is I all the way to j minus 1. So I use my reward minus my opponent's reward, and I take the max of them. I'm gonna see the max differences I will have with my opponents to check if I can win the game or not. And then I use recursive function to solve the function. And so if we only have this part of code, we will have like reach the maximum recursive function, right? So how do we stop the recursive function? Is by using the base case. So when I equal to j, and this means we only have one number left. So when I meet j, and that means we only have one number left, and that's the number we can pick from. And that's why we'll just return the value for that particular item. And that's the reward we can get when we hit the base case. And so let's go back to recursive function, and that's the core idea, right? So if I pick from the left hand side, I'll minus whatever my opponents can get. And that's the reward differences we got. And eventually we check, hey, is my reward minus my opponent's reward will be greater or equal to 0? If it does, that means I'm not gonna lose. As a player 1, I'm not gonna lose, and I'll return true. Otherwise, I'll return false. Otherwise, that means my opponents will eventually win the game. And that's how we solve the minimax algorithms. So, um, this is actually the templates that we're gonna solve for all the problem that we listed previously. And keep this in mind. But this is some people may like, hey, wait a minute. So, and the time complexity for this is 2 to the nth power, right? Because each number can belongs to player 1 and player 2, and I don't think a recursive function really helps to solve the question because it's way too time consuming. The time complexity is the worst. Yes, you're right. So now how can we optimize it? Let's check what are the things we can cache, right? So in Minimax, we typically cache whatever the variables are represents the state. So in this question, what is the representation for the state? It's actually I and j. And I and j are the variables that are moving around. And eventually, when we calculate the value, so we can cache the entire value that we already computed and to the variables, right? So in this case, we're going to use I and j as a cache and to optimize it. So this is the standard approach for dynamic programming with the top down, and we cache the value and we reduce the time complexity from 2 to the nth power to the nth square. And let's go ahead and check out what the code looks like. So the code is very similar, and all we have in the extra is the memo as a hash map. So it could be a hash map, or it could be a two-dimensional array to store or cache the value. In this case, I use the hash map. And once we have the hash map, we pass into recursive function. And if you check code, and it's very similar to the previous one. The only difference we have is the base case, right? The base case is identical, and before the base case, we want to double check if we already calculate I to j. So if this part is already being broke down and already being calculated, and we don't have to compute it one more time, and we just bring that value back from the cache, and that's exactly what we did right here. And once we bring back the value from the cache, and then we do exactly the same thing as the previous recursive approach. So we still take the number from the left, which is right here, and we still minus whatever the opponents can get. If I pick the from left hand side, my opponents can only pick from the from this part, which is I plus 1 all the way to j. And if I pick from the right hand side, my opponents can only pick from I to j minus 1, which is this part. I subtract them, and I store the value into cache right now. And then my cache will have my results, whatever the recursive function being computed, and then we will bring back the value and store it right here. And then so when we have the recursive function that calling different intervals again, and then we don't have to compute it one more time because we have the check right here in the cache. So if we already calculated, we just bring back the value from the cache, and that's how we solve it. And this is actually the templates for all the future problems, and then which I'm gonna go over later. But before we go over the following problems, right? Let's think about the other concern people might have. So some people may prefer a problem like, wait a minute, so you have your value minus your opponent's value, but I don't like the subtraction. It looks annoying. So is there a way that we can calculate just my score, my return, without thinking about my opponent? I think there's an approach like that. So let's go into the next slides and check how we do it. So the code is I think is still identical to the previous problem, but ignore this part. We'll come back to this part, right? And the n is calculate the length, and we do a memo. And in this case, it is a two-dimensional array to cache the value instead of a hash map. So they don't play a difference in Python. But in C++, I think when you have a static two-dimensional array, which will be faster. But I think in Python it doesn't make a difference, and the base case will be identical. We actually don't need this. We have the same base case, and if we already calculate the value, and we just bring back from the cache, and everything will be identical to the previous approach except this part. So let's go ahead and analyze what this part stands for. So we have example right here, y1 5 2 7 3 6, and as a player 1, you still can pick from very left hand side or from right hand side. So if I pick from left hand side, which is 1, and my opponents can pick either 5 or 7 at next round, right? So let's think about the choices we have. So let's step back and think about 2 options we have. So the options we have is pick from left hand side or right hand side. And the options the opponents have is to pick left hand side and right hand side that we never used. So think about the problem first. If I pick from left hand side, which is the num side, right? So I pick from left hand side, and then my opponents will have 2 options, which is 5 or 6, either from left hand side or right hand side. So let's say like if my opponents pick 5 first from left hand side, so 1 and 5 are being used. So the following round, what are the numbers we can pick? And now in this case, I can pick only from 2 to 6, which is I plus 2, because this is I plus 1 already picked by the opponents, right? And then I can only pick from I plus 1, I plus 2, which is right here. And this is actually the interval I plus 2 all the way to j. And let's go ahead and step back one more time. So if I pick from the left hand side, which is 1, and my opponents actually pick 6, which is the right hand side, and what are the number are left for me is actually from 5 to 3. And this is I, 5 will be I plus 1. And this is j, 3 will be j minus 1. And my opponents can also pick, I can also pick from I plus 1 all the way to j minus 1 if my opponents pick from the right hand side. So this is the choices left to me in the third round when my opponents pick from the left hand side, which is 5. And this is the options left to me when my opponents actually pick from right hand side. And this is what left to me, which is from I plus 1 to j minus 1. And now we understand the first part, and this part is the mirror reflection, right? If I pick from the right hand side, which is 6, if I pick 6, my opponents can either pick 3 from right hand side. So if she pick from right hand side, and then in the following round, I can pick from I all the way to j minus 1, which is right here, because this is j, this is gonna be j minus 2. And if I pick from right hand side, my opponents actually pick the first number, and then I can pick from 5 to 3 again, and this is actually I plus 1 and j minus 1. And I want to minimize my opponent's reward. I pick the smaller one for the recursive function for my opponent. Same thing right here. I pick the smaller value that my opponents can pick from. And I want to maximize the total return that I have. So I pick from left hand side plus the minimum value that my opponents can pick from. And then this is from the right hand side. Once we get the global maximum value, and we store the value, same thing, into the cache, and we go back to the recursive function and check. So score first will calculate, the entire recursive function will calculate the score, the return that the player 1 can get from the global game. And score first represents the player 1's total return, and the score total will calculate the entire reward we have. So for example, 2 kids play some candy games, right? They take candy from a pool, and this is the total pool of candy, and this is the first kids, the candies that first kids got. And now we take the subtraction, and that's the second kids, the candies that second kids got, and we compare if the first kids got more candies than the second kids, and that's how we solve the question. And very similar approach and different logic, but in the future flights, I'll still focus on this approach because it's much simpler to think about. But most of the problem can also be solved by using this approach as well. You can freely pick what are the options you want. And let's go ahead and check one more example. So before we actually dive in this question, right, let's go back and think about the summarization we have for question number 1, predict the winner. we have two restrictions to think about. First, as a player one, what are the options you have? In this case, we can either pick from left hand side or right hand side. And the second restriction is, if I pick from a number from the pool, and the second player cannot pick the number anymore. And that's the two restrictions. And let's go to the next question and check what the question is describing, right? In this question, I really can't believe this is actually an easy question. So I think it's a medium. So I think the reason it's easy, it's labeled as easy, is because the two restrictions are summarized as a bullet point right here. So let's check. Alice and Bob take turns playing game, with Alice starting first. Initially, there's a number n on the chalkboard on each player's turn, and the player makes a move consisting of choosing any x with 0 less than x less than n. So n mod x equal to 0. And this means x is a factor for n, right? So for example, n is 10, x could be 1, it could be 2, it could be 5, because n mod x has to be 0. And x, now we know x is a factor for n. So this is the restriction number 1. What are the numbers we can pick? The numbers we can pick is a factor of n. Okay, restriction number 2, replacing the number n on the chalkboard with n minus x. So this is the number you are given to your opponent. This is the number you are giving to your opponents, n minus x. So if you already picked 2, for example, n is 10, and you already picked 2, and your opponents can only pick the factors from n minus x, which is 8 in this case. And now, given the restrictions that we already know, let's go ahead and check the code. So still we have in this case, we have a one-dimensional array to calculate, because we only have one number, right? And we cache everything. So we use the cache, and then so when n is 1, there's no more factors anymore. So that's why we just return false, and that's the base case. And same thing, so if the values are already being calculated, and we just bring back the value from the cache, and everything's identical to the templates. And the only difference is right here, and that's the key part for Minimax algorithms. So we initialize a win variable as false. So if one of the game can make me win, so I'll use OR to make win as true. So all we want to make sure is one of the strategy can make the opponents can lose. So I start with win as false, and then I loop through from 1 to n. But actually there's an optimization. So because the numbers we can take is the factor for n, but the factor can only go from 1 all the way to n divided by 2 to the half. So for example, your number is 10, right? So your factor could be 1, 2, it could be 5. It cannot be over 5, because over 5 is already over half, and it cannot be a factor anymore. It is one of the optimization. But in this case, I just want to make it simple, right? So we go from 1 all the way to n, and we check each. So this x is confusing, because I should name this as a x instead. So let's pretend this is x. So we have x loop through 1 all the way to n. This is what given by the question, right? As long as my x is a factor of n, that's restriction number 1. And then my opponents can only pick the number for n minus x. Click on the folder. And this is the options that my opponents have. So if this return false, not false will be true. So that means my opponents will lose, and then I will win. So if I can find one of the factors to make my opponents lose, then I'll win the game. And that's the key part of this recursive function, and that's how we win the game. And this is an easy question. Let's move on to more examples. And Stone games. Stone game is a classic sequence of algorithms for Minimax. So there are 7 of them. So in this case, I summarized the 7 out of actually like 6 out of 7 stone games. So one of the stone game algorithm is actually solved by heap, so which I didn't list it right here, but I'll cover like all of them for Minimax purposes. So Alex and Lee plays a game with a pile of stones, and there are even number of piles arranged in a row, and each pile has a positive number of the stones, pile X, pile I. The objective of the game is to end with the most of the stones. So whoever gets to more stones, which are the values, right, will win the game. So the total number of the stones is odd, so there are no ties. Alex and Lee take turns, with Alex starting first. Each turn, a player takes the entire pile of stones from either the beginning or the end of the row, and this continues until there are no more piles left, at which point the person with the most of the stones wins. And this question, to be honest, I think is almost identical to Predict the Winner. I couldn't find any differences because the question is indicating that at each round, there are still 2 players, right? 2 players game, and we know this is a Minimax, and we can either pick from the left-hand side, which is the beginning, or the right-hand side from the end. So we can pick one of the stones from the beginning or the end, and it's not repeatable, because if I pick 5 and my opponents can only pick from 3, 4, 5, he cannot pick the first 5 anymore. So this is almost identical to Predict the Winner, so I couldn't find any difference. Let's just go ahead and check what the code looks like. Still, like, we initialize a hash map to indicating the value that we cache, and we pass the 2 index. One is from left hand side because we can pick from the beginning, and right hand side we can pick from the right, the end. And we don't need this, and this is just a redundant base case, and we have the base case right here. When x meet when I meet j, that means we only have 1 number left, and we just pick the number's value. And redundant base case, I don't think we need this, so I'm just catching an error that when num's given pile of stones are already empty. So this is the value I passed. I highly suspect that I already copied the code from the Predict the Winner because it looks so much similar. And the core idea is still, like, if I pick from the left hand side, and my opponents can only pick from I plus 1, because the first number is already picked by me, so he has to plus 1. And if I pick from the right hand side, which is nums j, and my opponents can only pick from j minus 1, because the right hand side already picked this particular number, and we take the subtraction and we take the max to maximize the differences. So if the differences is greater or equal to 0, that means I'm not losing, so player 1 is not losing, and that's how we win the strategy. I think it's almost identical. I couldn't find any differences. So I don't want to beat that horse, so I think we got this part. And let's check the stone game number 2. So now we change the name. Alice and Bob continues their games with a pile of stones, and blah blah blah. This is identical, and the only differences for this question is we introduced a variable m. Alice and Bob take turns, with Alice starting first initially. M equal to 1. On each player's turn, player can take all the stones in the first x remain piles, where x is greater or equal to 1, less or equal to 2m. And then m is the cap, and then we can set m equal to the max of m of an x. So now we already given the two restrictions, right? So the first restriction is we initialize the m equal to 1, and at each time you can pick only from the left hand side. There's no j anymore, there's only I, because you can only pick from the very beginning. You can pick from the very left all the way to the right. How many numbers you can pick, how many stones you can take from the pool from the left. You start with 1. You start with m equal to 1, and then you can pick 2m. So let's check one of the example, right? So for example, I'm the player 1, so I can either pick 1 or 2, because I'm initialized as 1, right? So we can take at most like 2. So I can pick either 1 or 2. So if I pick one of the number, in this case m will be still 1, and my next player can still the indicator m still gonna be 1 for my opponents. So opponents have m equal to 1, and he can only pick either 1, which is 7, or 2, 7 plus 9. So he can play the game with this kind of strategy. But what if in the first round I pick 2 numbers, because m is 1, so I can pick 2m, 2, right? So if I pick 2 and 7, so my opponents can pick 2 to the m. In this case, m is already the max of 1 and 2, right? So my opponent has m equal to 2. So she can pick 1 or 1, 2, or 1, 2, 3, or 1, 2, 4, because m is already 2. So she can pick 2m at most, so which is 4. But we only have 3 numbers left. So which means she can take everything, and then I'll lose the game. That's not good. That's not good. So I don't want to do that. So in this case, I feel like, as a player one, I pick less number. This is another example that local optimal solution does not guarantee the global optimal solution. So don't be greedy. Don't be greedy to take everything. All right. Now we understand the game. 2 restrictions, right? The first restriction is you can pick from the left hand side, and you can pick at most 2 times m, and each time the m is changing. So which is the second restriction. So what are the numbers you pass to your opponents? Now there are 2 things you are passed to your opponents. One is m. M is changing. And the second thing is your opponents can pick the numbers that never being used. So this is actually similar to the previous problems. So with these 2 restrictions in mind, now let's think about how we solve it, right? So in this time, we want to return the maximum stones that Alice can get, which is the player 1. So what's the maximum value that player 1 can get? So one of the optimization we can do in this case, right, is remember, let's take one of the example. So let's assume that this array is huge. It's like 1,000 or 10,000 elements right here, and I is already in the middle. But m is also very big. So for example, I is 500 and m is like 250. So 250 times 2 is going to be 500. So I start at 500 and the m can go all the way to 502. Isn't this player can take all the values at the back, right? So she can take everything in the back. But when you do the summation, so do you have to go through the 500 elements and doing accumulation, doing the summation for each of the elements? That's time consuming. But is there an easier way to do this? Yes. So we can use postfix summation to do some optimization. So we can initialize a pre-processing array to store the postfix summation, and then we can optimize the solution. So what is postfix summation? So it's the opposite for the prefix summation. For example, in this case, right, and we have 100, 5, 4, 3, 2, 1, and the postfix summation will be 100, 105, 109, 112, 114, and 115. So in this case, so if I call piles 1, it will be the summation from all the way to 2, 3, 4, 5, 10. So we don't have to recalculate the summation from 2 all the way to 100, because we already did accumulation from the back, and that's how we optimize the solution. So now let's check the solution. So in the beginning, I did everything in place, but this is actually bad practice. So I highly recommend you initialize a separate array to do some postfix summation for this. So I loop from the back to the beginning. I do some accumulation. In this case, when I call piles I from here, this is not stands for 2 anymore. This will stands for 2 plus 7 plus 9 plus 4 plus 4. And if I call piles I equal to maybe 2, and U stands for 9 plus 4 plus 4. So it will be the accumulation from that particular elements all the way to the back. So we have this process, pre-processing as piles, and we passed it in, and now we passed in 2 variables. Remember, this is not I and j anymore, because we cannot pick from the back. We can only pick from the beginning, so which is I, and the m is the initialization, that the maximum number we can pick from the very beginning. So how many stones we can pick, and these are the two variables we are passed in. So n equals the length of the piles. So we have I and m so as the variable right now. So we don't have j anymore. So we just use these two variables as a cache key. So if you already calculate this stuff, like we just bring back from the cache, everything is identical to the previous templates. And the only difference, there's a couple differences, right? So one of the example is the base case. So this is actually what I just described, right? When you have a huge array, for example, you have a huge array, and I is somewhere in the middle, but m is very big. 2 times m is already, plus your initial position, is already bigger than the entire length of array. So that means you can pick all the stones in one shot. In this case, don't hesitate it. Just take everything. You can take all the stones. And that's the base case. So now we understand the base case. Let's go into the key part, which is the recursive function. Now we are going through, so how many numbers we can pick? As the question described, we can pick from 1 stone all the way to 2 times m stones. So we try out every single option. So that's why we have the loop right here. So we can try everything we can try pick 1, pick 2, pick 3, and check which will lead us to win the game. Lead the player 1 win the game. So, and that's why we tried out everything. And then what's my opponents can get from this game? So if I pick, so this is the initial position I got, right? And if I pick X stones, and then those are stones I picked already. So my opponents can only start from I plus X, and that makes sense. Just like the previous question, right? The stone game 1, and I is gonna be there's no X in that case. We only have 1 because we can either pick 1 from the beginning or the end. But in this case, we can pick multiple. What are the numbers we can pick? They are X. So that's why we'll use I plus X. And what's my opponents can pick? The question is already giving it to us. So the opponents can pick the max of m and x. And that's what we're giving to our opponents. And then piles I will be the numbers we can get, and minus what opponents can get. And we cache the value, and then we use the recursive function to solve the question. Very similar to previous problem, so I'm not gonna beat that horse, but let's go ahead and check the next problem, stone game number 3. And this question is hard, but I hardly think so. I think this is a medium question, just like the first one. I think it's even easier than first question. So let's read the question. So Alice and Bob continue their games and blah blah blah. This is identical to previous problem. So the only difference is right here. Alice and Bob take turns, with Alice starting first on each player's turn, and the player can take 1, 2, or 3 stones from the first remaining stones in the row. Okay, so still we take the remaining stones, right, from the stones, right? But in this case, we can pick 1, 2, or 3. So like Bob can pick 1, 2. Oh, I'm sorry. Alice starting first, right? Alice can pick 1, right? And then Bob will take, Bob can pick 1, 2, 3. Obviously, Bob will take everything. But if you're Alice, you're smart, and you'll be thinking like, hey, we only have 4 numbers. I'll pick 3. 1, 2, 3. So Alice can take at most 3 stones, and Bob can take from the rest. But this is 7. That's why Bob is winning the game. So something like that. So I think the problem is self-explanatory, very identical to the stone game number 1. So I'm not gonna beat that horse again. So let's go ahead check the code. So we still initialize a memo, and then we do the same thing, calling the recursive function, and then we have the memo. But in this case, like we can only pick from the left hand side, right? We can pick 1 or 2 or 3 stones. So we just calculate the pre-sum. So if the value is already being calculated, and then we just take the value back from the cache. And if I is greater or equal to end. So we are already reaching the end of the array. So there are no stones left for us to pick. So we just return 0 in this case, and this is the base case. So we are looping through from 1 to 3 to 3. So this is not inclusive, that's why 4 is not included. So we only have 3 options. We can either pick 1 stones or 2 stones or 3 stones. 1 stone, 2 stones, 3 stones. So and we just have the presum to record that, right? So presum will plus or equal. This is just in case we are not reaching the boundary. So if we are reaching the boundary, just break from the loop. So if we are not, so we accumulate the values into presum. So we can pick one of the nums, and we can pick another, and we can pick another one. So at most we can pick 3 because the loop only loop like 3 times. So and we try out everything. At each time we accumulate the presum, and we calculate the differences we have. And presum is the value that Alice can get, the first player can get, and this is the following player can get. The following player can only get from I all the way to I plus X, because the first player already picked X stones. And we take the subtraction, just like the previous problem. And then the subtraction will indicating the differences for actually this is the wrong variable. That will be the diff. Actually, the differences between the first player and the second player. So if the difference is greater than 0, that means like Alice will win. If it's less than 0, then Bob will win. Otherwise, it will be a tie, just like before. So now let's go into stone game number 4. Still Alice and Bob are taking turns then playing games, and still Alice starting first. And I think the question is slightly different. So initially there are n stones in the game, and then each player takes turn. The player makes a move consisting of removing any non-zero square number of the stones in the pile. So now we are giving a number. I think this is very similar to Divisor Game, right? So we start with the number, and what are the numbers we are giving to the opponents? It's gonna be n minus the square number. And if a player cannot win cannot make a move, and he or she will lose the game. And super similar to the Divisor Game. So let's check the code. We still initialize the cache, and we initialize everything as -1. So if the value is already being calculated and it's not equal to default value, and then we just bring back from the cache, and everything is identical to the previous version. And the only difference is right here. I can pick a number I from 1 all the way to square root. The reason is that if we go beyond the square root, and the I square will be greater than n. That doesn't make sense. We do not want to pass the negative number, so that's why we only go from 1 all the way to square root. And n minus square root number, square number. And this is the number we pass to our opponents. So if the opponents can fail, so if my opponent does not win, then I win. So that's why I return true. So I memo this. 1 stands for true, and 0 stands for false, stands for lose. So I win. If none of the number from I all the way to square number makes my opponents lose, then I lose. So very simple game. Okay, let's check next one. Stone game number 5. There are several stones arranged in a row, and blah blah blah. Same thing as before, and still Alice and Bob. Let's find out what's the differences in this game. In this case, Alice divide the row into 2 non-empty rows, left row and right row. Then Bob calculates the value of each row, which is the sum of the values of all the stones in this row. Bob throw away the row which has the maximum value. Alice's score increased by the value of the remaining row. So if the value of the 2 rows are equal, Bob lets Alice to decide which row will be thrown away. The next round starts with the remaining row. The game ends when there's only 1 stone remaining, and Alice's initial is 0. So now this game is getting a little bit trickier, but still under the two restrictions to think about. So what are the first restriction? What are the numbers we can pick? Now we can pick a row. So how do we determine the row? The question indicates. So what the question is basically saying is we can split the array into two subarray. So for example, I'm the player 1. So I can split the array from here to have 6 as an independent array and the rest of the numbers as another independent array. Or I can split right here, 6, 2 as an independent array and 3, 4, 5, 5 as an independent array. And the second player is a jerk. So he's saying, hey, so if you wanna split in this way, I'll let you to throw away this number. I don't want you to get a bigger one. I want you to get a smaller one. Such a jerk. So get a smaller one, right? If I split from here, they'll be like, yeah, this number is still bigger, so I'll still let you pick this one. You got the idea. So the player 2 is determine what the player 1 can get. Basically, the player 2 is indicating you have to throw away the bigger value and kept the smaller value. And if I pick this from the middle, right? So this is 14 and this is 11. So I'll throw away the 14, keep the 11. And when it's player 2's turn, and then I will pick another. So he will split the array again, and then I'll pick which one to throw away. I'll also pick the bigger one to throw away. So that's the core idea for this question. So this is restriction number 1. So the restriction number 2, like I mentioned, is so when we throw this away and when we keep this part, and this is the array that we leaving out for the next player. So now we got a core idea. And how do we do this actually? So if we can pick split from here, from here, from here, from here, from here, why not just try out everything? So that's what we're gonna do. We're gonna try out everything. We're gonna split everywhere. And is there any optimization we can do? So for example, we split right here, right? And we have to calculate the summation from 6 all the way to 3. And for example, we have an array with 1,000 elements. We split from the middle, and we have to calculate the summation from 0 index all the way to 499 index. This is redundant. This O(n) time complexity. Nobody likes it. So there's a way to optimize it, right? So just like the previous questions, we use a postfix summation. In this case, we're gonna use prefix summation. So 6, for example, prefix summation for this is gonna be 6, 8. 8 plus 3 is gonna be 11. 11 plus 4 is gonna be 15, and 20 and 25. And with the prefix summation, so you can easily calculate the range sum. So if I'm gonna calculate 6 all the way to 3, so we use we just use the number right here to minus number right here, and then with the O1 time complexity, we can calculate the range sum. So it's just one of the optimization. Without this, you can still solve the question. So let's go ahead and check what the code looks like. So just like we described, we have the prefix summation, accumulate the value, and we still pass to index I and j, and we have the presum being passed in, and I equal to j. When I equal to j, there's nothing to split anymore, so we're not getting any values. So when I and j is being computed, and then we just bring back from the cache, all of these are the templates. All of these are like stirred up. So we don't need this part. So we don't have to care about this part. It's so easy. Now we focus on this logic, right? And the question is saying we can split everywhere. We're gonna try out everywhere, right? Let's do that. So from I to j, from the beginning all the way to the end, we split everywhere. So the K stands for that, right? The K stands for where we're gonna split. And once we split in the middle, for example, K, right? We try out everything with K right here. We split right here, and we wanna calculate the sum from the left or from the right. And that's where we mentioned about to use the presum to calculate the range sum, right? So we use, and this stands for the summation from I all the way to k and this is from where is that, from k all the way to j. So we split the array into two, and then we calculate the summation from the left hand side and the right hand side, and we check which one is bigger. And the second pair is a jerk. We already know that. So if left hand side the summation is bigger, the second pair will say, hey, I'll let you pick the right hand side because it's smaller. And the opposite logic right here. So if the left hand side is smaller, then that guy will be like, yeah, go ahead and pick left. So if they are equal, so they will let you decide which one to pick. And this is actually your logic. You will pick the bigger one and to win the game. So now we understand the logic, and the rest of the logic will be identical. And we cache the value, and then if we already calculated, we just bring back from the cache. So I think we got this part. So now let's move on to, I think, the last problem for stone game. This is actually easier question. So let's read the question first. Still, Alice and Bob playing the game as starting first, and there are n stones and blah blah blah. They're the same, and the only difference is right here, right? On each player's turn, and they can remove either the leftmost stone or the rightmost stones. They can remove from left hand side or right hand side from the row and receive the points equal to the sum of the remaining stones. So now the value you are getting is not from the stones that you removed, it's from the rest of the stones. Let's check one of the example right here. So if I pick 5, and then I'm not like picking 5 right now, I'm removing 5, and then I can get the values from 3 all the way to 3, 1, 4, 2. I can get the summation for this, and that's the restriction number 1. So I remove one of the stone and get those values. And the restriction number 2, I'm leaving these stones to my next player. And this problem is identical to stone game 1, only one slight difference. The slight difference is the stone game number 1 will pick a value, we get that particular value. But in this problem, we pick one value, we remove that, we get the rest of the value. So that's the differences we have. The rest of the logic will be identical. As you can tell, we need the summation from 1 to 3 to 1 to 4 to 2. It's another range sum. So still, we're gonna need a pre-sum to cache the value, do some like pre-processing, and so we can easily get the range sum with the O1 time complexity, and that's what we're gonna do. So we still have the pre-sum right here and calculate the pre-processing. We have the 2-dimensional array to cache the value, and we pass a recursive function index from I to j, and this will be same. And when I is greater than j, then that means like we don't have any number to pick from, so we just return 0. And the memo, if we already calculate the value, then we can just bring it back from the cache. Now this is the core idea, right? Remember the first question, almost identical to this, right? Except this part. So in the first question, we can pick nums I, nums j, but in this question, we are getting the rest of the numbers. So if I pick 2, then I can get the value from all the way to from 6 to 8. So from I plus 1 to, because we have the padding right here, so that's why we increment 1. This is actually from I to j. So we can pick from I to j, and we can pick from I minus 1 to j minus 1, right? And that's the summation we got. And then still we use the value, the values we got. This is the values we got, and this is the values that our opponents got. We take the subtraction and we take the max, and that's how we win in the game. Okay, so I think that's a good summarization for all the Minimax problems. So as you can tell, that to summarize all of this, and we only have to care about 2 things. So one of the restriction is, so what are the numbers we can pick, or what are the values we can pick, and what are the values we can leave out for our opponents. So if you grasp the key idea for these 2 parts, and then you can grasp the entire idea for Minimax. And really hope this video will help you guys. And Please don't forget to subscribe my channel, and I'll see you guys in the next video.